These are the answers to homework 3B. Here are the definitions I would like you to know. Now let's go to the questions. Number 1, predict whether each of the following processes will be spontaneous, non-spontaneous, or it cannot be determined. Number 1, A, an exothermic process in which the disorder increases. We can determine whether a process is spontaneous or not by determining numerically the value for delta G. If it's a negative number, the process is spontaneous. If it's a positive number, the process will be non-spontaneous. An exothermic process is one in which delta H is negative, and a process in which disorder increases has a positive value of delta S. This would make, on the right side of the equation, the first term negative, and the second term would be negative because of the negative sign in front of it. Both terms are negative. That means delta G has to come out to be negative. The process would be therefore spontaneous. B, an exothermic process in which the disorder decreases. Exothermic process means delta H would be a negative value, but if the disorder decreases, that means delta S is a negative value. In this case, our first term on the right side of the equation is negative, but the second term is a negative of a negative. That's a positive value. So these two terms are opposite of each other, and that means that delta G cannot be determined without knowing the temperature, and so therefore this would be undeterminable. C, an endothermic process in which the disorder increases. An endothermic process, the delta H value is positive. If disorder increases, that means that delta S is a positive value. In this case, the first term, delta H, is positive. The second term is a negative of positive. It's going to be a negative value. The two terms are opposite of each other, and therefore delta G cannot be determined unless you know what the temperature is. D, an endothermic process in which disorder decreases. Endothermic processes, delta H is positive. If disorder is decreasing, that means delta S is negative. In this case, on the equation at the top, on the right side, the delta H term is positive, and the second term is a negative. A negative is also a positive term. Both terms are positive. That means delta G has to be a positive value, so therefore this process would have to be non-spontaneous. Number 2, using data from handout 5, what is the standard free energy of formation of barium oxide solid, and then what does it mean? So looking this up, you would find that the numerical value for the standard free energy of formation of barium oxide is negative 552 kilojoules per mole. And what does that mean? That's the free energy change when you form 1 mole of barium, when you start with a container that has barium in it, oxygen at 1 atmosphere pressure, and barium oxide in it. All three are present. And when all three are present under standard conditions, because the value is negative, it means the forward reaction is spontaneous. So when you're doing free energies, it's a little bit different. It's not the energy change when the products turn into the reactants. It's when starting with a container at 298 Kelvin, having all of the reactants and products present in their standard states, the forward reaction will be spontaneous because in this case, the free energy change turns out to be negative. Number 3, for the reaction at 298 of silver with mercury 1 chloride forming silver chloride and liquid elemental mercury, use data from handout 5 to answer the following questions. First, calculate delta H naught for this reaction. So using our tables, we would look up the standard enthalpy of formations for the products and the reactants and go products minus reactants. So first, to calculate the enthalpy change at 298, we would start with the product side, 2 moles of silver chloride multiplied by its standard enthalpy of formation, then plus 2 moles of mercury multiplied by its standard enthalpy of formation, and that's an element in its standard state, so it would just be 0. Go to the reactant side, minus 2 moles of silver multiplied by its standard, or its absolute standard enthalpy of formation, which because it's an element in its standard state is 0. And then minus 1 mole multiplied by the standard enthalpy of formation of mercury 1 chloride, which is negative 265 kilojoules per mole. We cancel out the moles in each of the terms. The answer is going to wind up coming out in kilojoules, and I get 11 kilojoules as the answer for the enthalpy change under standard conditions for this reaction. B, what's the standard entropy change? We're going to go to the thermodynamic table and just look up the entropy values of the products and reactants. Starting on the product side, 2 moles of silver chloride multiplied by its absolute entropy of 96 joules per mole Kelvin, plus 2 moles of mercury multiplied by its absolute entropy of 76 joules per mole Kelvin. Notice nothing zero here. That would violate the third law of thermodynamics, which says the only substance that has a zero absolute entropy is a perfect crystal at 0 Kelvin. Over to the reactant side, minus 2 moles of silver multiplied by its absolute entropy of 43 joules per mole Kelvin, and then minus 1 mole of mercury 1 chloride multiplied by its absolute entropy, which is 196 joules per mole Kelvin. The moles cancel out, the units come out joules per Kelvin, and I get 62 joules per Kelvin as the entropy change for this reaction under standard conditions at 298. C, calculate delta G naught. We can use the free energy of formation values in our table and just go products minus reactants because the temperature's at 298. The table works for any reaction at 298. So looking up the standard free energy of formations, I go 2 moles of silver chloride multiplied by its standard free energy of formation of negative 110, then plus 2 moles of mercury multiplied by its standard free energy of formation, which because it's an element in its standard state is 0. Over to the reactant side, minus 2 moles of silver multiplied by its standard free energy of formation, which is 0 because it's an element in its standard state. And then minus 1 mole of mercury 1 chloride multiplied by its standard free energy of formation, which is negative 211. Moles cancel out. The answer comes out in kilojoules, and I get negative 9 kilojoules. D, calculate delta G naught from delta G naught equals delta H naught minus T delta S naught. So just giving you a second way to calculate delta G naught at 298, we'll use our answer from A, the delta H naught value of 11 kilojoules, minus 298 Kelvin multiplied by my answer from B, which converted to kilojoules per Kelvin is 0.062. The Kelvins cancel out. I'm combining two terms that are units are both kilojoules, which is perfect. And my answer comes out negative 7 kilojoules. If you notice, answers from C and D aren't exactly the same, but they're pretty close. You'll sometimes have a little bit of disagreement between the two methods of calculating standard free energy changes, but they would theoretically be the same number, and they are pretty close. E, is the reaction spontaneous under standard conditions? Whether we calculated delta G naught in problem C or problem D, they both came out negative numbers, and that's what's important. If the value for delta G naught is negative, that means the forward reaction is spontaneous. And because we're calculating delta G naught, we'll say the reaction under standard conditions is spontaneous. F, did the enthalpy change and the entropy change work for or against spontaneity? Well, we have to look at their signs. So the sign of delta H is a positive value. That's working against spontaneity. The sign of delta S is a positive number, and because it has a negative sign in its term, that works for spontaneity. So we would say delta H works against spontaneity because it's positive, and delta S works for spontaneity because it's positive, and that second term has the negative sign in front of it, making that a negative term. G, which factor predominates? Well, in this case, because the reaction is spontaneous, the delta G value is negative. The one that works for spontaneity was the one that predominated, and so therefore the entropy term predominated over the enthalpy term. H, what is the delta H naught for the reaction at 375 Kelvin at a different temperature? Well, if you want to calculate the enthalpy change at a different temperature, fortunately, the enthalpy change at any temperature, in this case 375, is just exactly equal to what you would have calculated from the thermodynamic table 5 at 298, so therefore the answer is just 11. I, what is the delta S naught for the reaction at 375? If you want the entropy change of the temperature other than the one given in the table, fortunately, because entropy is not temperature dependent, it's temperature independent, it's going to exactly equal the entropy change value you calculated at 298, so that's just going to be 62. J, what is the delta G naught for the reaction at 375? This is the one that is temperature dependent. And so therefore, if you want the delta G naught value at 375, you have to calculate it from delta H minus T delta S. So using our two values, 11 kilojoules minus 375 Kelvin multiplied by 0.062 kilojoules per Kelvin, I calculate a delta G naught value of negative 12 at 375 Kelvin. Number 4, For the reaction at 298 Kelvin of bismuth reacting with bismuth 5 oxide to form bismuth 3 oxide, use the given data to answer the following questions. So here's the reaction we're dealing with, and question A says calculate the delta H naught for the reaction. So using only the data given, there's actually enough standard enthalpy of formation data to calculate the delta H of the reaction by just going products minus reactants. Starting on the product side, to calculate the delta H naught of this reaction, we're going to go 5 multiplied by the standard enthalpy of formation of Bi2O3. Now we go to the reactant side, minus 4 moles of bismuth multiplied by its standard enthalpy of formation, which because it's an element and it's in its standard state, it's solid at room temperature, that would be 0. And then minus 3 moles of Bi2O5 multiplied by its standard enthalpy of formation, which is negative 604 kilojoules per mole. Moles all cancel out. The answer comes out in kilojoules, and I get 727 kilojoules as the delta H naught for the reaction. B, calculate the delta G naught for the reaction. We have enough data given in the table to do that, so I'm going to do it the same way, products minus reactants. Start on the product side, 5 moles of Bi2O3 multiplied by its standard free energy of formation of negative 257. Go to the reactant side, minus 4 moles of bismuth multiplied by its standard free energy of formation, which is 0. And then minus 3 moles of Bi2O5 multiplied by its standard free energy of formation, which is negative 689 kilojoules per mole. Moles all cancel out. This comes out 782 kilojoules. C, calculate delta S naught for the reaction. And in this case, enough data was not given to you because I left out the absolute entropy of bismuth, which is not a value of 0. So you cannot do this by going products minus reactants. You have to do this using delta G naught equals delta H naught minus T delta S naught. And we're going to solve for the delta S naught of the reaction because we know the other 2 thermodynamic functions. So the delta S naught will be delta G naught minus delta H naught over negative T. So if I plug my answers in from A and B, divide by negative T, I get a value of negative 0.19. That's because when I subtracted the 2 numbers in the numerator, 782 minus 727, I wound up getting a 2 significant figure number in the numerator. Then when I divided it by 298, my answer has to be 2 significant figures. So it actually is negative 0.19 kilojoules per Kelvin, or you could say 190 joules per Kelvin. D says calculate the standard, D says calculate the absolute entropy of elemental bismuth, the value that wasn't given to you in the data in the problem. So how do you do that? You're going to use this negative 0.185 kilojoules per Kelvin. That's the delta S for the overall reaction at the top of the slide. That will equal the entropy of the products minus the entropy of the reactants. So watch this. If the overall reactions change in entropy, delta S is negative 185, that would equal 5 moles of Bi2O3 multiplied by its absolute entropy, which is given in the table on the problem, 69 joules per mole Kelvin. Then subtract 5 moles multiplied by the absolute entropy of bismuth. This is the one we didn't know, so make it X. Minus 3 moles of Bi2O5 multiplied by its absolute entropy, which was given as 94. And now you have one giant equation. Every number is known except for the absolute entropy of bismuth. And if you can do a little algebra, you should be able to solve for that. And I get X equal to 62 joules per mole Kelvin. That would be the absolute entropy of the bismuth. Number 5, final problem. For the phase change, liquid bromine turning into gaseous bromine, A, use data from handout 5 to calculate the standard change in enthalpy for the phase change, which means it's heat of vaporization. So to do that, we're going to go products minus reactants in this reaction, looking up the standard enthalpy of formation of the 2. So starting on the product side, 1 mole multiplied by the standard enthalpy of formation of gaseous bromine, which is 31, minus 1 mole multiplied by the standard enthalpy of liquid bromine, which is 0. That's a good problem to think about what we mean by standard state, right? What's bromine in its standard state? It's diatomic, and it's one of the 2 elements on the periodic table that's a liquid at room temperature. So the reactant is the one that has a 0 value for its enthalpy of formation. Br2 gas is not in its standard state, so therefore it doesn't have a value of 0. So you look that up in the table, you'll actually see it's 31. So this comes out 31 kilojoules as the heat of vaporization, or the enthalpy change of vaporization. B, using data from handout 5, calculate the standard change in entropy for this reaction. So we'll just go products minus reactants. So 1 mole multiplied by the absolute entropy of gaseous bromine minus 1 mole multiplied by the entropy of liquid bromine. That comes out 93 joules per Kelvin. C, calculate the standard free energy change, delta G naught, for the reaction at 293, and tell if the forward or reverse reaction is spontaneous at this temperature. So we're calculating delta G naught at a temperature other than 298, so we're going to have to use my delta H value and my delta S value to calculate it. So the delta H naught at 298 is going to equal the delta H naught at any temperature, so it'll equal the value at 293, so we already know that. And the delta S that we've calculated at 298 is the same at any temperature, so we can use that. And so the delta G naught at 293 will equal 31 minus 293 multiplied by 0.093 kilojoules per Kelvin. Kilojoules minus kilojoules, this comes out positive 4. So that means if you're at 293, which is 20 degrees Celsius, that means the reverse reaction is spontaneous. And so therefore, gaseous bromine at room temperature would condense into liquid bromine, which is how it's naturally found at room temperature. That would kind of make sense. D, calculate the standard free energy change for the reaction at 353 Kelvin, which is a much higher temperature, and tell if the forward or reverse reaction is spontaneous. We'll just do it the same way. Now at 353, it's going to be 31 kilojoules minus 353 times 0.093 kilojoules per Kelvin. Kilojoules minus kilojoules, I get -2. And because that's a negative value, then at this elevated temperature, way above room temperature, the forward reaction is spontaneous. So if you have hot liquid bromine, it's going to turn into gaseous bromine. It's going to vaporize or boil. E, calculate the boiling point of the liquid bromine. The important concept here is the boiling point is when the liquid and the gas are in equilibrium. And if this reaction's at equilibrium, that means delta G would be 0. If we really want the normal boiling point, which is what I should say in the problem, then that means that the pressure of the gas in the reaction has to be 1 atmosphere, and it's under standard conditions, so therefore delta G naught must be 0. So if delta G naught must be 0, and I know delta H naught is 31, and I know delta S is 0.093, the only thing I don't know is the temperature. So using the fact that at equilibrium, delta G naught is 0, if I solve for the equilibrium temperature, that's going to be the temperature that's at equilibrium for the reaction at the top of the slide, which is the reaction for the boiling of liquid bromine, which will be its boiling point. So 31 kilojoules divided by 0.093 kilojoules per Kelvin, and I get a boiling point of bromine to 2 significant figures of 330 Kelvin, which would round to 60 degrees Celsius. And if you want to look that up on Wikipedia and see if it's right, then you'll be amazed and stupefied.